So what about the rules with mirrors? So we have a concave mirror here. If we have an object closer than the focal point, you've already seen before that there's this focal point and the center point, which is twice the distance of the focal point. So a parallel ray would go straight through the focal point. So that's again the same rules. Parallel goes through focus, and a point coming from the center would be directed back to the center. And this way you can work out what happens. Well, and another thing is also a ray that seems to be coming from the focus, which would be this direction, of course becomes a parallel ray like this. And all three rays give you a virtual position here, which would predict an upright virtual image behind the concave mirror, like this, virtual upright. We have a convex mirror. We put an object, for example, here. What are the rules there? We have a parallel ray. It will be reflected as if it was coming from the focal point here. So we have to draw it like this. If we have a ray that is directed towards the center, it would be reflected back in its original direction. And if we have a ray that is directed towards the focal point, it will be reflected parallel to the optical axis, like this. So we get a virtual image and it's upright here. So what about thick lenses? In the case of thick lenses, we have to be a little bit careful because now we have two planes at which we have to apply the law, Snell's law, basically. And so how do we construct this? Well, we can replace that lens with a virtual surface like this here, which is called the principal plane, at which we simply pretend there was a thin lens. And so this would be the front focal distance to what is called the first principal plane here. So front side first principal plane, at which a ray from the focus would seem to be bent. If we basically look from here backwards, it looks like this is the bending position. This is how it is worked out. And then if we have a parallel ray that focuses to a point here, we can also define another principal plane at which this bending seems to be happening, and we get the back-sided focal distance here, and this is the second principal plane at which parallel planes seem to be bent. And so now we have two different rules for parallel beam that focus to another focal point. Well, on the other side, at a different plane, that's the main point, compared to the ones that come from focus. So we need now these two principal planes to draw what happens in thick lenses. So here's an example. If we want to work out where the image with a thick lens is formed, we take the parallel beam going to the second principal plane, we let it go through the focus here, as we've just learned, whereas the beam here that goes through the front focal plane goes to the first principal plane and then becomes parallel. So this is where our image formed. So what do we do now with the diagonal beam that previously didn't do anything? Well, now there's a new rule. We have to sort of teleport it from the first principal plane to the second principal plane and then continue parallel to the original direction, and it will then also cross in this position. So here's our image. Of course, similar to a thin lens, it's an inverted real image that we have here. So the part about aperture stops and pupils and windows, I will not really go into, but we will straight continue with the topic of aberrations. So first of all, we'll do an experiment of spherical aberrations.